Hello everyone, Mike with Spray Jones, and we're coming back to you with video number 2 now in our roof and spray foam series. Video number 1 covered the vent and not to vent, and I thank you to everybody that has subscribed, checked that video out, and commented and given us some feedback. Now we're going to get into really the sense of cathedralized attics and the science behind the whole roof system, take a more advanced look at it, because I think that most people wouldn't argue that spray foam closed or open cell makes a lot of sense in a cathedralized ceiling where you're limited on space and slope, and it's a steep slope. But what about an open attic? What about an attic where we've got lots of space, it's cavernous, it's a huge plenum? What do we do with that? And that's what we're going to get into today. So as always, thank you to everybody that's subscribing and joining the channel. I really appreciate it, and I really like talking to everybody around the world. It's kind of neat. All right, on to this report by Craig DeWitt. He makes a very interesting statement here. This is a March 11th, 2002 report, and you're going to notice a common theme here, that a lot of the reports that we're going to get into are 20 years of age or sometimes even older. So this is nothing new. Structural benefits of spray foam. Clemson University has been researching the use of spray foam as an enhanced attachment system for roofing. This research centers on how to retrofit or construct buildings to be more resistant to hurricane and other high wind events. Clemson's research shows that spray foam can significantly improve the attachment of roof sheathing to trusses and rafters, similar to the way construction adhesives help bond a roof or a floor system together. In a retrofit case, foam can be sprayed on one or both sides of the sheathing and rafter intersections from inside the finished roof. In new construction, spray foam can be applied to the entire roof system, and that's what we're looking at. The spray foam makes a significantly stronger roof than either nails or screws alone. More information on this research is available from Clemson University's Civil Engineering Department in Charleston, South Carolina. I agree. We have seen an enormous amount of truss stability from the spray foam insulation, and we're going to really get into the cathedralized attic system today with all of the benefits that it brings. So we're going to scroll down here to where he talks, because this report covers a number of different things. It's sort of an overview of foam insulation, but I want to concentrate on the roof here. Insulating the underside of the roof rather than the ceiling creates many other benefits as well. Historically, we ventilate roofs in an attempt to prevent moisture problems and reduce heat buildup. Current research shows that much of the moisture in attics comes from damp basements, crawl spaces, as well as the living space. I showed that in the previous video. Research also shows that if we address the crawl space, basement, attic, and living space moisture, we do not need to ventilate an attic. In fact, by ventilating an attic, we can often make a moisture problem worse. I agree. I said that ventilation is a cruel mistress. Attic moisture problems are a result of moisture condensing on cold roof surfaces. Adding more vents causes the attic to be cooler, especially at night, which causes more condensation to form on the underside of a cool roof. Cutting a hole in the roof causes a bigger hole in the top of our chimney, which makes the chimney draw better, pulling even more moisture upward. I have not seen any attic moisture problems solved by adding attic ventilation, with the exception of ice damming. Ice damming is warm attic phenomenon and can better be addressed by reducing the amount of heat leaking into the attic. Unfortunately, the building codes have not kept up. Attic ventilation to reduce summer heat buildup in the attic has also been challenged recently by research done by Florida Solar Research Center and the Building Research Council in Illinois. Much of the heat in an attic is from radiant heat transfer. The hot sheathing radiates heat to the ceiling or other objects in the attic. To cool an attic, outside air is vented through attic or insulation is added to the ceiling to prevent the attic from heating up, warming up the living space. Research shown that the attic ventilation would have to be quite large to make much difference in attic temperature. In summer, the best you could possibly achieve was outside temperature. With a very large fan using lots of energy, you might get close to outside temperatures. In winters, this would result in colder attic temperatures as well. Skipping on down here, he says a roof system insulated with spray foam reduces energy in several ways. Energy loss from ducts located in the attic is essentially eliminated. The top of the building is much tighter, resulting in less infiltration, exfiltration, so excess moisture isn't pulled into the attic. Infiltration through the ceiling is also reduced. In addition, the attic temperature is lower, which further reduces energy loads. That's huge. We're going to get into that maybe in this video, but for sure into the second one. We're going to get into heat loads and does it really cost more to do it this way as far as what you're going to be paying to heat or cool. In a standard insulation system, ceiling insulation reduces heat transfer from the attic to the living space in the summer. Attic temperatures can often approach 140 degrees Fahrenheit during the day. Most of this heat enters the attic space through a multi-step process. First, solar energy warms the shingles and the sheathing. The hot sheathing then transfers heat to the rest of the entire attic through conduction, convection, and radiant heat transfer. The 140 degree Fahrenheit temperature of the underside of the roof surface drives the heat transfer process. By insulating the roof surface with spray foam, the surface temperature exposed to the attic, the temperature driving the heat transfer is reduced by as much as 40 degrees Fahrenheit. Both conduction and convective heat transfer are proportional to a temperature difference, so that heat transfer will be reduced proportionally to the point in surface temperature. Radiant heat transfer, though, is proportional to the fourth power of the temperature difference. The reduction in radiant heat transfer resulting from an insulated roof can easily exceed conduction and convection reductions. So this PhD and professional engineer is telling us that there's a structural benefit to the roof, that there is a massive thermal benefit in stopping the heat from coming in and making the attic space hot, which negates other methods that we're going to try to use to keep the attic cool, such as ventilation, and that we're dealing, thirdly, with eliminating a moisture problem, since the most common problem of moisture in the attic is not a lack of venting, but it is air leakage from inside getting into the attic space and creating the moisture problem. So we've seen here on an engineering report that it makes sound sense on three major points: structural, air leakage, and attic temperature, to be insulating the underside of the roof deck. Now we'll skip over to a well-documented ASHRAE report for moisture drive. Now this is an older report. This is 2002 ASHRAE. ASHRAE stands for American Society of Heating and Air Conditioning Engineers, and they're going to cover cathedral ceilings and attic ventilation. And I want to skip down to page 3. I've gone through this report and read a lot of it, and there's a lot of information that we don't need to go over. We just wouldn't have the time in the video. But let's check this out. Picking up here, he references a test done by someone by the name of Samuelson, demonstrated that if no air is moving from the living space to the attic, the higher temperatures in unvented attics makes these attics drier. So the context is moisture buildup within the attic and the need to vent and to cut down this moisture drive. So he stated here that no air is moving from the living space into the attic. The higher temperatures in unvented attics make these attics drier. Interesting. However, he stated that to guarantee no indoor air movement into the attic, the ceiling has to be airtight and the pressure of the attic air needs to be higher than that of the indoor air, i.e., example, pressurized attic and a depressurized living space. All right? So you understand what he's saying? You got to keep the warm, moisture-laden air out and down in the living space. Or we solve this with spray foam insulation. Paragraph 2. In addition to a framed cavity with porous insulation material such as glass fiber, and I would add to that cellulose and mineral fiber. They're all in the same family, folks. Other constructions deserve attention, such as roof systems with foam thermal insulation which is relatively vapor impermeable, applied directly to the underside of the roof sheathing when foam insulation is used in walls and low-slope roof systems. It generally demonstrates good moisture performance. In a sloped roof system, equally good moisture performance should be expected when the foam is directly applied to the sheathing and carefully sealed. There is no moisture performance advantage to venting such roof systems when the foam is located on the top of the roof deck or the roof is made of structurally insulated panels. Venting is also unnecessary. Boom, there it is, right in the ASHRAE journal. Venting is unnecessary. So I think we're starting to see the case that we can have a cooler attic in the summertime, we can have a warm attic in the wintertime, that the warm attic dries out the attic space and keeps it drier. We can then pressurize the attic space with the interior temperature and the air movement within the assembly, and we have an all-round better system. And now we're going to take a look at what exactly our cathedralized attic space should look like. This was the report that I initially got my hands on. I think I first saw this in 2004, and I was like, yes, 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 the Spray Polyurethane Foam Alliance, and God bless these guys. They're doing great work in all of North America, but United States primarily. They had a coalition of people here on the board, the Building Envelope Committee members, John Stahl and Laverne Dalgleish here, Kafka member, Canadian Urethane Foam Contractors Association. I've met and sat with Laverne many times when he was still involved with Kafka. But here's what we want to take a look at. Closed cell spray polyurethane foam may be used to construct unvented cathedral roofs. Yeah, we know that. And cathedralized attics. That's what we're talking about. It can be applied in sufficient thickness to satisfy local energy code requirements. Now, just park on that for a second. I'm going to come to that in the next slides. Directly to the underside of the roof sheathing between rafters or joists of any slope in all heating, mixed, and cooling climates. This configuration controls the entry of moisture-laden air into the insulation and also eliminates dew point occurring at the underside of the roof deck and anywhere in the insulation in all heating, mixed, and cooling climates. And then they have a caveat down here, assume that you put it on thick enough to do that, which is a no-brainer, but there's a lot of people out there with no brain. Due to the fully adhered closed cell properties of SPF, air and moisture are displaced out of the insulated space, including at rafters and sheathing. You see this? The moisture are displaced out of the insulated space, including the rafters and the sheathing. So the rafters aren't soaking up moisture, folks. The sheathing isn't soaking up moisture. It's not sitting there holding it, and the spray foam's holding it back and holding it in place where it would normally not be. That's not what's happening. It's displaced and it's gone. Moisture cannot enter the insulated space from any direction, eliminating the requirement for roof venting. And we sort of saw that with what the ASHRAE manual said and then what that RLC engineering said. Venting above the closed cell SPF could reintroduce moisture-laden air into the new airspace below the roof sheathing, which may introduce another moisture condensing point. Therefore, venting above the SPF in these configurations is not recommended. I agree. I do not get into this, let's just put the vents in anyhow to satisfy something. Folks, either you are going to get on with this engineering or you're not. You cannot have one leg in the new system and one leg in the old. You cannot be trying to use typewriter technology with your iPad, laptop world. So, you don't need the vents, get rid of them. You need to have the engineering in place. If you've got some building code inspector that's telling you it needs to be vented and you have to install vents and you haven't done your homework, and you're going to need to get into that. And we're going to talk about that later in this video, how to wrap all of this up and what to do. So let's take a look at the detail that they prepared. This is the SPFA's cathedralized attic detail. So we all understand the conventional flat ceiling here, and normally our loose fill insulation or batted insulation would be placed on here, but instead we're showing the closed cell foam. Now, in climates, I suggest that the closed cell foam be used for probably 90% of your non-vented roof details. And what makes a difference is if you are far enough south in the U.S. where you get into the warmer climates where the vapor barrier rules are not there, where the closed cell foam can be legally installed on its own without an additional poly or spray applied, liquid applied vapor barrier, then go ahead. Like, there's the engineering is there and behind it. Icynene has done a lot of studies on non-vented roof assemblies and the use of open cell foam. But for most of us, if we're in extremely cold environments, or we're going to have hot and cold, we've got seasonal changes. So if you're in Illinois, you're in New York, you're in the East Coast, Massachusetts, Alaska, upper Northwest, I think closed cell is by far the proper choice. Likewise, too, if you're down in Florida, I think closed cell is the choice just because of hurricane. Anywhere where you're going to get down into the south and you're going to get into hurricane loads, I think closed cell has the structural advantage over open cell. So I don't think closed cell is ever the wrong choice. The reason people shy away from it is just cost, and my answer to that is pony up the cash and do it right. Not saying that open cell isn't doing it right, but it's clearly the better product is closed cell. So some things to note here. We're right to the underside of the deck. They are not showing installation of vents whatsoever. You have to have your rafter heel blocking installed, recessed, like I said, to the outside. This joint would be caulked and air sealed. Your spray foam would be brought down. Those of you that are spraying in cold weather climates, watch the top of the plates when things are getting frosty and cool outside. This is a proper or a common area where things like to disbond slightly if it's going to be damp. All you got to do is dry it up, get some air movement through there, and make sure that it's well sealed and well adhered. You're always going to be going over top of the cords, but we're not going to build the full value of whatever we're spraying, the 3 or the 4 inches, directly over the cord. And there's a number of reasons why. One of them is the capillary action of the foam is not going to allow us to be spraying on 90-degree surfaces very easily. But notice what they say here. In cold climates, embed metal connector plates in spray foam to prevent wintertime condensation. This is an absolute must. Now, I've seen some engineer groups that have actually specified to have a minimum of 1.5 or 2 inches over top of the plates. That's fine. I don't have a problem with that. Go ahead. But for sure, everybody, metal connector plates direct to the outside that are attaching to the top cord bearing absolutely have to be embedded in foam, and they should be embedded 360 degrees around. Don't leave any metal exposed to the inside or they're going to drip. This is a common mistake of rookies. They just don't understand that this needs to be what it needs to be. Now, I promised that I'd talk to you about code. Energy codes for most people on flat ceilings are going to be somewhere in this R35, 40, 50 range. We all understand this, right? We're all frustrated by this. This is the number one reason why you want to do a cathedralized attic detail in anywhere where you are in the US or in Canada. The rule designations you are going to find in most of your states and counties and in provinces, you have a totally separate set of rules for this, for vaulted ceilings, for cathedralized ceilings. When you are following the slope of the roof deck, the requirements for the quote-unquote R value are less. So guys, installing foam. You want to stop getting beaten up on having to spray so much closed cell foam. Stop trying to put it down here on the sheetrock. It does not belong down here on the sheetrock. That is my opinion. But I also have some really good facts behind why that is. How are you going to get into here? I have a whole video dedicated to getting inside existing attics once the sheetrock is up. There's a couple of real big problems with this. You can push the drywall down. You can fall through the drywall. All the penetrations have to be installed. The attic is still vented, so it's still freezing cold, so you can't do this seasonally. Here's your advantages to doing the cathedralized attic. One, I've never had a building code official turn me down on holding me to about an R30 value for the underside of the roof deck. So now I'm not at R40, and I'm certainly not at R50. So I just get my engineering group to write me up what it's going to take me to get to an R30 value on the closed cell foam to the roof deck. So right away that rolls me in better. Secondly, in the middle of winter, with the exception of extremely cold days, this can all be closed in. Roof vents aren't in, soffit venting is closed in, the sheathing's on, the shingles are on, the penetrations are through the roof, and what do? We heat the structure up with heaters. And the hot air goes which way? Straight up to the underside of the roof deck. Warms this roof deck up. You got nice hot air. It's always going to be 10, 15 degrees Celsius more warmer at the roof line than it is at the entry level at your ankles, right? So we start at the roof, we work our way down, we get a first pass on that roof deck, and then from there it's a cap. It's a foam cap over top of the building, and it's keeping the building warm. So if this was a conventional vented system, I'd be letting all my hot air out and escaping. So the other thing that we like seeing with this is that the foam is embedding the top cord completely in spray. So you're getting the structural support out of the roof sheathing, and you're locking and stress locking in the top cord. The top cord has nowhere to twist. So truss uplift and truss twist happen when the top cord is freezing cold and contracting, and the bottom cord is super warm. So there's a temperature differential between up and down, and it begins to twist the top cords. All right, we see that in cold climate where they can actually pick the bottom cords up even. They'll start to bow and arch, and they'll crack and break the ceiling. So we don't have a problem with truss uplift when we're putting in the spray foam closed cell to the underside of the roof deck. Folks, this is marketable. Guys, this is highly marketable if you are sprayers. I have got guys that make this into storage all the time. I have storage in my attic. On 712 pitch, you can just about walk down the middle of the attic here. You can get people to start putting plywood down and sheeting. You can get a few lights up inside there, temporary lighting or lighting that's on a switch. You get an attic hatch that drops down with the old-timey ladder in it, and you can get up in there and you can put all the winter clothes, the summer clothes, all the bulk items of life that take up extra space can go up inside the attic space. This is not living space. It never is deemed living space. In our building code in Canada, it's exempt from needing the thermal barrier, provided you're not putting the mechanical equipment in it, or you're not designating it as storage space. So our builders will never ever call it storage space on the plans and never show it that way, but it is rigged up in such a way that somebody after the fact they've taken possession can come in and make that into storage space. I've had lots of people do that, and that is a really good way to go. The other advantage that you have is that all of your pot lights can be standardized non-insulated canisters. You can put speakers in. You can put TVs dropping down out of the ceiling. You can do all sorts of mixed coffers and internal vaults. You can mix it up. You can have this part flat, and then you can coffer it, or you can have it go up vertically and over. You can have a ledge or what have you. All of that is just interior finishings. This is, in essence, a suspended ceiling. It's inside the warm zone, and you're not messing with the envelope. So I believe that the cathedralized attic space really is the superior way to go. And we're going to take a look at a couple of details now on some construction for homes and see how we would do them and what else would make sense and how we do the details. Just before we get into these details, let's take a look at some comments of what people have said on previous videos dealing with the unvented roofs. He Knows writes, all I know is my house was cold, I had my attic spray foamed, and my house is toasty, and my power bill went way down. I could care less what the roof looks like. I'm warm and saving money. See, if the cathedralized attic space and roof was costing you a lot more, you wouldn't be seeing these kinds of testimonies. Do these comments, Blue Archer writes, do these comments still apply to a roof of an 80-plus-year-old house? I'm having lots of trouble figuring out the best insulation retrofit practices for these older construction techniques, U.S. Climate Zone 4. Yes, absolutely. We have retrofitted an enormous amount of 100-year-old, 110-year-old homes. It's the only way to deal with them. The brick, the old siding, they're not meant to be vented. And we've got excellent success with sealing those up. But that'd have to be a dedicated video for retrofit homes. Tony writes, I guess I should know this since I have a conditioned attic space with closed cell foam sprayed to the underside of the roof. Best thing I ever did. coastal northeast. So there's a testimony that it's really working well. Jack Marr has been watching for a long time. Closed cell on the bottom, peel and stick or fluid applied on the top. I'm pretty sure you will never have any problems. Your thoughts? He's just talking to the underside of the roof deck, and then peel and stick and fluid apply. Yeah, that's absolutely a really good way to go. We're going to get into that in videos 3 and a little bit more in videos 4. We're going to get into roof underlays and all these different types of products, but absolutely stop the water from the outside and then control the condensation in the water from the inside. No brainer. Chris writes, we have open cell sprayed to the underside of the roof deck. It was done in 1998. The roofer did a poor job and many nails missed. These small leaks were not big enough to drip below, but big enough we noticed soft spots in the decking. Rather than take the roof off and deal with the soft decking, we installed nailed 1x4-inch purlins through the shingles and put on a metal roof. There is now a 1-inch air gap between the original roof and the metal. Not only did this solve the leaks, but the house is noticeably cooler in the summer. We're in Indiana, so summers are very hot. Okay, they're very good testimony is why I picked this one out. That it's not the end of the world, folks. And I mean, the foam is not causing premature advanced failure. They're saying, look, we had some dripping below, but not big enough that we noticed soft spots in the decking. So answering the question of should we only be using open cell so that we can tell whether we have a roof leak, this dispels that right there. You're not always going to notice it. So if you'd had closed cell to the underside of the roof, you'd have an additional structural support, and it might change what you want to do. But this is a really good solution that they did anyhow. Main contract, general contractor, I would assume a roof with lower than a 312 pitch would have an EPDM or greater roof covering and would allow for the same and similar detail. He's talking about non-vented to the underside of the roof deck, and you're correct. Waterproof to the outside, stop the water from wrecking the decking, and then the thermal insulation is to the underside, and you've got a great system. So just getting into the promise that I put about compartmentalization. What if you're a spray foam contractor or you're the homeowner or the general contractor and you want to take care, you're sold on the idea of the spray foam non-vented system now, cathedralized or vaulted or mixed thereof, but your client's just not going to spring for it for the whole entire roof. What do? Here's a good example. It's vaulted. It's got a little bit of an attic space at the top. We've seen that. Very, very common. Over here, conventional attic space. And maybe they want spray foam for this, but they want to blow this in. What are you going to do? It's very simple. You see this truss right here? This rafter needs to be sheeted. You need to have the framers plywood sheet this down to the outside wall. And then you're going to put your spray foam to the underside of the roof deck, no vents. And then you're going to have to tie in and completely seal and make sure your envelope goes all the way and attaches at the top over to your demising wall. And your internal demising wall within the attic is then going to be built up 2, 3, 4 inches thick of closed cell. Now, something that I usually do, folks, if my spec is 4 inches closed cell on the roof or 5 inches closed cell to meet my requirements, I'm not going to necessarily do that on my demising walls. I'm going to treat my demising wall like an outside wall, and whatever my specs were for an outside wall, I'll treat on the vertical surfaces. And I think that's only logical and fair. And let's be blunt, the only reason that we're doing so much is to try and encapsulate more of the cords anyhow. 3.5-inch deep top cord, we're going to be using 3 to 4 inches of material anyhow. So you would compartmentalize this side, and then these would be sprayed. And you'd spray them from the back side so it's not going to interfere with the detail of the drywall or what have you. And that, I mean, how are you going to crawl inside there and get it from this side? It's a little difficult. So usually come in around the back side. It's nice and open. Spray it generously onto the deck, encapsulate everything and bring it down, making sure that everything touches. And that if you have any doubts about overlap, just go generous. Just get an extra foot on one side or the other side, and then you know you don't have any cold lap. Pretty common standard stuff. Continuing on with a little bit more look at detail, parallel cord, but then the truss system has been designed to have a flat ceiling. you're not going to try and spray foam down onto here or do a mixed blow-in. I'm going to get the client to go right from the heel all the way up, right to the peak, and I'm going to have things blocked in and situated in such a way that the spray foam is going to come all the way from the top, all the way down, and get everything sealed. Now here's a really good example over here. It can be very, very, very difficult to get spray foam up into these tight little areas. So if you find areas where you're spraying up here against the underside of the roof deck and you're getting tighter and tighter and tighter, you've got to have people go and cut. We carry a Sawzall, but we'll get the framers to do it ahead of time and the builder to do it ahead of time. We'll get them to cut out. I call them beaver tails, where they got extra. They'll sheet this so that the trusses can piggyback on top. But you can't get in there. You physically can't get in there. So we get them to cut large, generous access holes so we can see 100% of the roof deck. Because whatever we give up in the plywood, we're going to gain with the structural support and rigidity of the spray foam. So get these things cut out so that you can be assured that you're getting your spray foam 100%. The underside of the deck and the hollow spots, the shadow areas behind these top cords all need to be sprayed. It's easy when you're standing here below, but you can't get up inside here. This is just a really good example of why spraying up and dealing with everything without the sheetrock in place just totally makes sense, because you can address every single issue visually. Everybody can visual and make sure you've got everything into all the tight spots, and then you get to close everything up. If you've closed everything up, who's the person that's going to be going around and checking inside the attic space? Well, it's only going to be the spray foam guy. And he's up there and he's hot and he's cramped and he can't move around. He's getting his hose caught on everything and he's upset and he wants to get out of there as soon as possible. And that's a recipe for making a mistake. And I really, really believe that the sheetrock should not be up. You shouldn't have to make multiple trips. We're there to spray long before the sheetrock is ever up, and that way everybody can visual everything and make sure that it's detailed properly, and then your drywall goes up. Another detail here. All right, this is classic. All right, so here's your conventional blow-in system, and here's why it's so flawed. You would think about blowing R40 or R50 down here on the flats, right? But then what are you going to be getting in these walls, these bedroom walls? Certainly not R40, certainly not R50, and it's open face to the backside where it's vented. So we typically hear of people saying, well, the bedroom's so cold. Well, of course it's cold, because you don't even have plywood sheeting in a house wrap. Usually they'll put some sort of horizontal strapping to keep the bats from falling out of here, right? But there's no way to stop the air and just the air movement moving through it. It's death by 1,000 cuts or a wind fan at this point. Okay, this is also a technical problem with, they'd have to plywood sheet this. They can't just put a soffit here. They've got to put an insulation stop here. I had one builder that had a detail where the roof went out over top of the veranda a lot, and he opted to get blocking put in and then spray foam put down the roof deck and across the blocking and onto the plates. And in this situation, that's exactly what we did. We'd have the framer. There's probably going to be a vertical support inside the attic here. It doesn't show it in the drawings, but these aren't rafter and truss drawings. They're just the overall drawings of a house to be built. We would want the builder to give us vertical plywood here, nailed into place, solid, and then we'd bring the spray foam totally down the roof deck and all the way down onto the plate. And then these walls here for the bedroom are walls in the middle of space, and they're going to be extremely warm. And this is actually fully usable storage space if they want to plywood sheet this. We had one person that had this detail, and what they did was they put recessed shelves and they put recessed drawers into the attic. And they had all the kids' toys in their bedrooms. They had these deep 2-foot long supported toy boxes that would roll out of the wall. And they loved it, folks. They loved it. See, if you're spraying down and trying to spray the back of this and then spray back up here again, you're not taking advantage of the spray foam system. You're not thinking like a foamer. You're thinking like a bat and poly guy. You need to get with the times and get with the new thinking. And you need to be able to give your clients marketable advantages as to why they're going to use this more expensive system, this better system. And this all becomes storage in warm space. And it's not dead air space because it's going to equalize with the rest. Like if you sheetrock this floor, this open web floor truss, if you sheetrock this, what are you doing to circulate the air inside the floor? Nothing. It equalizes on its own. Is it a different humidity level? No. Is there a moisture problem in there? No. Is there a dust problem in there? No. So to think that this absolutely has to be power ventilated or tied into the HVAC system is flawed thinking. It does not. It's going to equalize on its own. Now, what some code official is going to call for in your area, that's a total separate issue, and we'll probably get into that in video 3, because video 3 is going to be dealing with HVAC up in the attic and all that sort of stuff, cubic footage of air and stuff like that. Here's an example, new construction. Home builder actually came to the homeowner and said, if you want to be putting in this many pot lights, as you can see here, and some of these, this is a speaker. We got a speaker over here, one over here. If you want to put this many penetrations into the structure, then we want to go spray foam to the underside of the deck. Because my builder has learned that this is a recipe for air leakage and condensation issues, and therefore switch it to closed cell foam to the underside of the deck, and he can put whatever he wants all the way through here, and no big deal. And that's what we're going to close out on here. We're just going to deal with a few through the roof penetrations and what you should and shouldn't be doing. Okay, this is another example of solving two problems with the spray foam closed cell. This is a vaulted ceiling, and this would be a vertical wall exposed to the inside in the house that would have to be batted. So you would have this blown in or batted, and then they would have to bat this, and then there's actually a vertical or horizontal exposed shelf in the house. We've seen this before where there's a ledge, which is here, and then there's a vertical wall of drywall that's 2.5 to 3 feet, and then it finishes out the vault. This is to combine two roof lines within the house. Normally this would have to be batted. With the spray foam, it's all warm space, and you don't have any problems, and you don't have a weak spot of this not being your R40 or R50 and having condensation issues. But what I want you to see is, one, connector plates at the top are all embedded in foam. My guys go around all of them. And then two, any plumbing stacks that you have going through the roof, they're going to have some sort of an expansion, rubber expansion joint on them so they can move up and down and what have you, left and right. But we come down the plumbing stacks 2 feet. So here it is at the roof deck, and then they're coming down 2 feet. That way any cold air that's dropping down the plumbing stack cannot condense, frost it up on the outside, and drip water back down. And by the time you get 2 feet down, or 1.5 feet, we've just made a rule, 2 feet. If we've got the 2 feet of space, we'll come down 2 feet. There's no way that the air at this point past the 2 feet is cold enough, it's warmed up enough coming down the pipe that it can't cause condensation and dripping inside. So any of you guys spraying into cold weather climates, anybody getting this kind of work done, make sure your spray foam guy has gotten all the metal connector plates. Obviously these connector plates are in warm space. They're not going to condense. You're only concerned about the connector plates to the outside, the top cord that bears the weight. Those are the ones that all have to be embedded in foam. All these middle ones, they're non-existent. They're no big deal. Just want to make sure I say that, because probably somebody will lay a comment otherwise. Here's just a close-up. I found another shot of a plumbing stack that's been roughed in. Obviously this is in a, here I'll back it out so you can kind of see. This is in a corner of a wall. Here's the outside wall and drywall edge, and we don't have the 2 feet to come down it like we normally would based on a bathroom or something being right there. So this is the best we could give them and still have enough room for tie-in, and that's a really good way to go. Best of my knowledge, never had any issues with it. And then this is a fireplace rough-in for an actual wood burning stove. And that's the final couple of things to say, is to be very careful with high temperature gases coming out of fireplaces. If you're going to have a wood stove like this, they had an insulated canister roughed in ahead of time and blocked in, and then we bring the spray foam up to it and around it on the sides of the blocking, and we don't venture in. We don't even venture into this box. If they want this box air sealed, my recommendation is to use the high temp silicone and to have the furnace or fireplace guys, I should say, caulk this and air seal it when they come to hook up the pipe, and they're going to be using their high temp silicones. If you're dealing with zero clearance piping for fireplaces, what have you, got to be checking what the outside temperature is. Most of those are running at 80 degrees Fahrenheit. If that's the case, then you're going to be okay to bring your spray foam up to it, provided regulations in your state, county, and province allow to. Here's a really good example. We had a person with a fireplace, wood burning fireplace, and the pipe coming out of it was jacketed and insulated. Now, it had a big sticker on it, and it said, "Do not put combustible materials on this." And I phoned the fireplace manufacturer that installed that, and I said, what do we do about it? And they said, there's an insulation ring, a jacket, a steel sleeve. Bring your spray foam up to that steel sleeve and not past it. And then from there, we take care of the rest. And that's what you got to do, because you cannot be putting spray foam in direct contact with something that's going to be at 400 degrees Fahrenheit. But the outer jacket, the insulation ring, never got above, I think it was 90 or 100 Fahrenheit or something like that. So it was well within the range of what the closed cell foam can do. And that is the insulation stop that you're designed to do. And something that he noted to me was that after they take care of that, after we spray up to that ring, they caulk and air seal on the inside. They caulk with a high temp silicone to air seal this so that air from inside the box isn't easily leaking through and getting into the chase and stuff like that, which causes condensation issues. That's a little bit more of a tricky. This isn't a video on that. It's just mentioning here your plumbing and your zero clearance and your high temp. Got to be careful. Special attention has got to be given to this kind of stuff when you're the spray foam installer, or if you're the homeowner and the home builder. You're going to have these details worked out ahead of time. Don't leave these details as a oops, we forgot. It does happen occasionally, but you know it's going in. Sometimes the clients change their mind, say, oh no, we want to have this instead, and they got to hack stuff out. Then you might have to get the spray foam guy back, clear out enough of the spray foam so that you can install the proper pieces, install the blocking, then get your spray foam guy to come back in, reseal it. Okay, that's just a change order. But if you know what's going in and there is no change order, get your prep work done ahead of time so that the guy isn't going to have some issue and you're not going to have condensation issues. So we're going to kind of wrap up this video now. We've taken a good long look at the Cathedralized system and some details and separating things out. We're going to go into video 3 here, and on the next video we're going to take a more advanced look at the following things: frost lines on the roof and the science behind it, utilizing zip insulated roof sheeting. We'll take a look at metal roofs with underlay, no underlay. Do we put underlay? Do we not? Do we put exterior sheathing or not? Shingles, of course. We'll take a look at the cubic footage of air that's being heated or dealt with inside the attic spaces, and what does that have reflecting on heating loads and cooling loads. How exactly we can sell these types of things or justify these things when clearly the amount of footage to insulate on the sloped roof is much more. And then I think we'll take a really good look at whether we're causing vapor issues. Again, take a more advanced look at the vapor drive, the air leakage drive, and the big topic, thermal barriers in attics. Do we need them? Do we not? And what do we do if we're going to be putting ductwork in the attics or not, or mechanical equipment in the attics? So that's going to be video 3. We'll also take a look at some really good comments people have laid out where they've got some really good scientific evidence and information that we'll be checking out in between then and there. So thank you for staying this far in the video. Thank you for continuing on your education with Spray Jones, and we'll look forward to the next one. And I'm really anxious to hear what your comments are going to be on this video, good, bad, or otherwise. And I'll catch you on the next one.